Now, one of the reasons one of the reasons we know we have these quantized energy or these quanta of energy or these different energy levels is because how these electrons exhibit light signatures. So if you energize an atom, if you give it extra energy, you call those electrons to get excited. What happens is those electrons actually jump to higher energy levels. When they jump up to a higher energy level, okay, so let's say, for example, if they jump from the second or from the first energy level to the second, or from the second to the third, and so forth, as they jump up, they absorb energy. Okay? Now, that absorbing energy gives them what we call an excited state. That excited state is very unstable for an electron. It doesn't want to be in an excited state. It wants to be in its ground state or its stable configuration. So what happens is, as soon as that electron jumps up, it absorbs its energy and then it falls right back down. Okay? So it goes from jumping up to falling down, and then when it falls down back to a different energy level, which gives it a very specific amount of energy that gets released. So it jumps up, gets excited, then they immediately fall back down to a lower state, releasing energy. Now, it always releases energy in these packets of light we call photons. Most of the energy gets released in the visible spectrum. They do some of it does get released in the infrared or the UV, but we see these packets of light being released in the visible spectrum, which means we can see it or track it. So here are 4 different elements: argon, helium, mercury, and neon. And we see that they exhibit these bright line spectrums where you have a lot of energy being released at this particular wavelength or a certain amount, and this particular wavelength, and so forth. So because electrons have quantized energy or set amounts of energy to them at their different levels, when they fall down, they always fall down and they give off a certain color of light, which we see as these bright line spectrums. Okay? Because we see the bright line spectrums, we know that the energy isn't spread out over a long range. It's actually very specific to very specific lines or very specific wavelengths that's in there. Okay? Now, if we jump to this website, I like this little applet because if you notice, here's an electron, it's hanging out, spinning around, and if I make it jump up, I give it some energy, it can jump up to a higher energy level. If I give it some more energy, it can jump up to another higher energy level. But then if it falls, when it falls down, the distance it falls creates a very specific wavelength of light. If it falls down again, I get a different wavelength of light. If I jump up again, I absorb more energy, and if I fall down again, I get another different wavelength of light. So every time it falls, it creates a band of light that we can see and track, okay, through a spectroscope. We can jump up, and then we can fall down, and we get another band, and so forth and so on. We can jump up, and we can fall down. We can jump up, and we can fall down. Okay, now this one actually goes off the chart, so it's not part of the visible spectrum. Okay, this happens billions upon billions upon billions of times a second anytime you're giving an atom energy. Okay, think of lights inside of your house, fluorescent lighting that's inside a school or inside your house. This is what causes the light to come off of those things. Neon lighting and all those signs we see, this is the same deal. We're giving electrons extra energy, they jump up and they fall down and emit light back in color patterns that we can see. Okay?